I'm oceanographer. I'm not a robotic guy as you, so my audience is a little bit different from the other conference that I usually go. However, I think it's a very interesting to be here and to explain our, at least our needs to you. And I think I want to pass the message that we need to communicate more. And this project that is very small, it's an interesting project that I believe will increase this type of communication between the science, in this case, oceanographer like me, and you guys, the people from robotics that work with the AUVs, UAVs, and other assets. So my presentation is about river plumes. Most of my work that I did during my PhD was about the river plume in the Douro River that is very close to the city of Porto, actually across the city. And after my PhD, I started to work with LSTS, the lab in the University of Porto, and then I started using AUVs, UAVs, and all of that assets that they use. So, well, this is my presentation outline. First, I will explain a bit of the basics of river plumes, present some background results regarding the Douro River one. After that, I will present some preliminary results that came from the surveys using AUVs and UAVs. In the end, I would like to talk a bit about how it's important to promote local and interdisciplinary projects or side projects in your labs like this one, and how they can help on the preparation of more challenging and demanding projects on the sea or in the deep sea. So first, river plumes are coastal water masses of lower densities. Most of them are with lower density because came from the river, so the salinity signal is lower. And they can carry several dissolved and suspended materials with distinct properties from surrounding ocean waters. Even the color could be completely different. So this is an example of the Fraser River in Canada. So you can see the plume zone, the ocean waters, and the interface of the water mass that is the front. They have also impact on coastal circulation, on biology, of course, and on morphodynamics because they can carry sediments. So in the case of the river, just a brief introduction. So it is the third longest river on the Iberian Peninsula. The river flow is heavily regulated by dams, and its average monthly discharge is quite variable depending on the winter or summer conditions. The estuary of the Douro River is located near the city of Porto, and the tide is mid-diurnal and mesotidal. That means we have 2 high peaks and 2 low peaks during one day, more or less, and the tidal range is between 2 meters and 3.5, depending on the neap and spring tides. So most of my background work results from images of remote sensing and numerical modeling results. And I use that to know more about the propagation of this plume. I use also traditional in situ observation like CTD casts and ADCP data that mostly for model validation because they are relatively old, so it's very hard to find in some of the coastal regions in Europe to find good data. And also they are limited on space and in time, and were designed for different purpose. So the people that went there, they are interested in other questions, so they are not thinking on the river plume propagation in that case. Here are some of the numerical results and the typical patterns of a river plume. We can see here that this is the typical pattern of the river plume without wind. However, the wind reveal a rapid response on the plume with that forcing. So depending on the wind direction and magnitude, the plume can be deeper, shallower, and can propagate towards all kind of directions in the coast. So it's not easy to survey this kind of feature. So you have different pattern on time, on space. So even to use AUVs is a challenging task. So now we are interested in study the smaller scale processes using remote sensing also, numerical modeling again, but also observations from AUVs. In particular, we are motivated to the study of generation of internal waves on the river plume front. This phenomena was only fully documented for the Columbia River in the US. So as surface waves, internal waves are waves that can propagate in the interface of two fluids. In a stratified ocean, like this case, they can propagate between two water masses, so the river, or at least the river plume, or in other masses in front of the river plume. So internal waves can play an important role in transferring heat, energy, and momentum in the ocean, especially in vertical, and their mechanisms of generation, propagation, and also breaking are still unknown in the ocean. We have evidence of nonlinear internal wave generation in Douro from satellite imagery. So here's one example from an image from, I think it's Sentinel-2A, yeah. In the green channel. It's with very, very high resolution, so 10 meters per pixel. It is possible to observe that here is the plume water mass, and then we can see trains of waves radiating from the plume. So this image is very similar to others collected from Columbia one. However, the Douro is about, or the river flow from Douro is about 10 times smaller. So to know more about how internal waves generate in low discharge conditions like this, it becomes vital to collect in situ data information and have a kind of snapshot that only AUVs can gather. I'm talking about snapshot in like a section or cross frontal section of the plume. To do that, so also to set up moored system or moored instruments here are challenging task because of the winter conditions in Portugal coast. You can imagine like 5 meters wave, 6 meters, 7 meters, so it's a little bit rough to work on that conditions here. So that's why we opt to do like, or plan regular and small missions with AUVs. Another example, so this is a RGB color, we can see the plume, and then smaller internal waves, or train of internal waves, now with more contrast, and we can see here the length scale of that wave, so the wavelength is between 50 meters to 100 meters. These are kind of small. In deep sea, some of them can reach an amplitude of tens of meters, so 100 meters. From the engineering part, there is also a need for small and short sea trials. So the people from LSTS usually work on this side, in this harbor, Leishon's harbor. It's perfect to perform some tests, but technological tests. However, well, for us, it's a little bit short. And if you go to the coastal environment with the scientists, so if you are alone working, you don't have like a oceanographer in your here, like, yeah, can you do that? Can you do this? And this type of training in communication is very important when you go to the open sea expedition, when you have limited time. So it's a kind of pressure that maybe it helps you in the future. So these new short operations are new for to test and use also the coordinate vehicles of LSTS. We can actually map and survey river plume at a fraction of the coast of the boat, using a boat, of course. However, this comes with the challenge of working with limited comms, while at the same time having vehicles adapting to environmental conditions. This type of operation is perfect to identify flaws and opportunities in systems because in this type of objective-oriented tests, you have a fast feedback from the end users. So these are the first results when we deployed just one LAV to do a simple zone-on transact in the river front towards offshore. The mission was synchronized with a satellite overpassing. In this case, TerraSAR X from German Special Agency. So here we can see, so the AUV starts here doing yo-yo, and we can see the temperature, salinity plots, and depth. So in the plume zone, we can see that there is a strong variation in salinity, but there is some point that the variation is, well, the range is very lower than this. So this is the ambient water. So we try to imagine how the plume is, so maybe like this, because of the typical pattern. However, when we check the satellite image, it's a little bit different. So we are perform here, the section, and the plume was like this. We can see in more detail. So we just cross the northern border of the front. And this is an example of how important to understand also the synaptic situation of the phenomena. So we also cruise the front, but where in space or when in the front that we cross. Analyzing the CTD data after, we can identify in the salinity plots a very shallow plume and the front also. And we can see the thermocline here, and also a deepening of the thermocline in front or in the frontal region. From lessons learned from this first deployment, we actually run on a surface currents that were very strong near the river mouth, so we need to be more careful when deploy the AUV there. We noticed that the vehicle was extremely heavy, so actually we didn't thought in, oh, maybe it's a buoyant plume, so maybe we need to adapt to the UV. So that alerts the law of operation for other missions that maybe we need to think on that when we are on the mission. And we just have two transacts that cross the front. And that's why we went for a new approach with the NEV autonomy increment. It consists of an onboard algorithm for the UAV autonomously detect, track, and survey the river plume. So the tracking algorithm was implemented by horizontal zigzag, like this image, and also yo-yo when done vertically. AUV zigzags alternate between seaward and landward sweeps to radial track the front as it moves over time. 5 yo-yos are done after the AUV cross and detects the front, and then vehicle makes a turn to cross it again. That trajectory to when they come to the land always go in the river mouth direction, so it's the source of the fresh water. And detection scheme here is very simple. It's only based on a surface salinity threshold that we defined by a prior analysis. So we did a CTD profile first. We know the salinity threshold, and we include it on the onboard algorithm. In this way, the AUV can map the river plume front vertically at the surface and a long time. Meanwhile, we also test, so in that way, in the feedback of users in real time. So after 1, 2, 3 missions, we also test new service like this one. It is possible to follow the mission from anywhere in a web service. Here is a snapshot from the Ripples that we call our web service. So Ripple's website, where it's possible to see 2 AUVs doing that yo-yo, and one starts here and doing this, and the other starts here and doing that. Um, since the acoustic and Wi-Fi comms were limited here in this new mission, the control and command mostly rely on SMES, one close to the coast, or Iridium message. So it's another training for a lot of operators. So they need to work in just with Iridium, and that came with some kind of problems, because when you control by Wi-Fi, you have the answer from the vehicle very fast. But with the Iridium, you need to learn how to wait, and like the anxiety of the maybe the vehicle is not answer, maybe not. And this is a perfect example how we can try that in a short and small project than in OpenSea expeditions. These are the first results from the algorithm. We got more than 15 cross-frontal transects from just 2 AUVs in 6 hours operation. Unfortunately, we didn't get any good satellite image because of the cloud cover in this case, and even the SAR, the radar image, we have problems with the wind. However, we also found, and then we also found that we waste too much time to find the first position of the front, because we start the algorithm inside the plume near the river mouth, but then if the plume is propagate very far from the river mouth towards south, the AUV takes a lot of time to reach the front. So we think maybe we can use an AUV to that first assessment. We have it. We need to test the coordination between that 2 different assets. Why not use in this situation? So we look forward to that and to use that to map the river plume. So these are the first assessment of the front location using a UAV picture, simple RGB. We just tilt the camera because of it's easy to see the reflection of the sun in the surface, and the front have like a convergence zone that the reflection of the sun is a little bit different, so you can see very easily the front, even if the color of the waters are not different, as you can see here. And we just communicate, or the UAV operator just communicate by telephone to the boat guy and say, hey, the front is 10 kilometers over there. But you can also go forwards or towards another type of missions, like UAV can detect by thermal image or RGB, and pass the information for the AUV. So it's like an increment and test methodology in a small project like this that could be useful for the future. And we can also continue to validate the data from the AUV using the UAV data. Here is the same location. So here is north, this side. So the photo is taken from here, and you can see that AUV data from surface, this line could match with the line of the front of the AUV. So it's pretty good way to validate our data and our algorithm. As I mentioned before, the development technological tools benefits from this type of collaboration, of course. And another example, the ripples that I talk about, this is from a mission that we worked on the last week. So the people on shore, even my colleagues from research, my advisor, can follow the mission even not being there. So they can see the data like this, because during the River Plume mission, we noticed that it could be nice to have like a glimpse of the TS data, like salinity and temperature plots. And the software team noticed that it could be feasible to do that, or to add that information on Iridium message. Even it's not the old data, but sometimes to make some decisions, we don't need all data. We just need a glimpse of how the profiles of the temperature and salinity are, and to make a decision like, well, the AUV cross the area that I will interest, we can stop it and not waste time and doing another thing. Um, so the results of this tool are quite amazing, and these results are also used in SOI expedition that João Sousa talked about yesterday in the lecture. So in that case, when AUV is operating 60 miles away from the Falcor, we could continuously check how data looks. And if AUV passes through the subtropical front, we can stop it and doing another plan or send another plan for the AUV. We also develop a NetCDF feature to upload files like satellite images as layers on the Neptus control and command. So like me, end user, I can command AUV, but over a map of ocean data. So I can do the plan over a front on the satellite image. And for me, it's more visual to see the AUV plan on that. Scientific outcomes from this small project. One of most important, it was the possibility to use the in situ data from the AUV as initial condition for a non-hydrostatic model to know in detail the generation mechanism of internal waves in the river plume front. For that, so this is the model. You can see the plume waters, ambient waters. And you can see that here the front collapse and acts almost like a piston here in the thermocline beneath the plume, and these waves propagates freely from the river plume front. So after its form, it propagates freely towards sea. And these are the internal waves, an amplitude of about 2 meters, so beneath the surface. It's not wave surface, so it's beneath the surface. And why we can see that internal waves on satellite imagery? Because as you can see here in the horizontal velocity, this type of pattern or internal waves propagation generates convergence and divergence patterns even at surface. So when we see these at surface, the convergence patterns aggregate material or generate different formations in the water because of the tension of the water. So what we see on the satellite, these lines are like convergence and divergence features. So it's not different material, it's just a manifestation or surface manifestation of internal waves. And that's how we can see from the surface that there is something that this propagates like 10 meters above the surface or beneath the surface. It's also important because the convergence zones can aggregate, for example, oil spills. So sometimes the oil spills aggregate in lines like this if there is internal waves, or surfactants, blooms, for example, if there is internal wave propagating over a bloom, can aggregate phytoplankton in that lines. So in future developments, we aim to use a dynamic threshold as a salinity gradient instead of a single value. Testing other possibilities out of the zigzag algorithm to have more orthogonal cross-frontal transects. We can do some frontal speed estimation using 2 coordinate AUVs without any fancy sensor, just CTDs. So we go to use cheap AUVs. So these are kind of risk, small projects, so no money for that. So just use a LUV with the CTD and how to estimate the speed of the front using that. More land-based operations, so why not deploy the AUV inside the harbor and just check the operation through the ripples and then the AUV come again? And that is particularly important for winter conditions in Portugal. Front detection from AUV using thermal and RGB imagery. autonomous coordination between UAVs, AUVs, and also ASVs. Um, autonomous possibilities to deal with the non-AES traffic. I don't know how, but that is important because we have several problems with small boats, fishing vessels, and that kind of feature. With AES, it's okay, but non-AES, it's a problem. Um, create an historical data set from a specific line. So we love time series. Oceanographers love time series, so we want to know the changes over the time. So if you do a test doing in the same location, so if you are, for example, here working in this location, well, try to use the same line over the time. And that data, if you use CTD or chlorophyll, can be useful for someone. If you test here and then there, and that data is very complicated to analyze and to get something interesting for the science. So if you use some specific position or location to test, choose a line and run the test in that line. AUV adaptive planning based on numerical prediction. So we use a lot of numerical modeling, so why not use that data to use in adaptive planning of AUVs, and also in the opposite. So having real-time assimilation from the AUV data on the numerical modeling. So this type of projects is perfect to promote dialogue between the scientists and engineers in the stress-free environment like this one. So it's a safe place to fail. So the open and very big projects is not very good place to fail at all. So it costs a lot of money. So maybe we need to work together in this type of projects before going to the sea or in the open sea. It's easy and fast to get feedback from end users. In most of the mission, we have enough space in the boat to invite another scientist or one or two people from different areas, but with the same interest in marine science. This increased the local collaboration among different institutions, promoting the brainstorming for new and large-scale projects. And this is important. This is not. There is no money here, but from the brainstorming, there is more money from the big ideas that came from the all or together we can raise. These missions are also perfect to short sea experience for undergraduate students. It's kind of difficult to have open position in the sea to marine scientists, like undergraduate students, to have opportunity to go to the sea. And these improve your dissemination and your outreach through the labs from the marine science. People have tendency to depreciate, but the bureaucracy have a lot of time consuming, as you know. So this type of project is perfect to establish new procedures. So flight authorization, boat rental, insurance, these kind of problems you can try here, and if it fails, okay. And this also improved the engineering team engagement. I believe that it's easy for you to work when you have a kind of objective or a final objective. So I think you have more engagement on the mission if you have like a scientist or a oceanographer or someone that say, hey, that is very interesting. We can use that. I think if you have someone beside you, it's like this, like that one, would be perfect to improve your confidence and to work in more projects like this one. So in less than 2 years with this collaboration, these short operations to survey the Dory River plume was indirectly involved in brainstorming for other completely different projects. For example, the Doris is a project that aims to develop an ASV for measuring surfactants and at the Ocean River interface system. And RAMP, it's a rapid response to marine pollution project, integrator that the main object is to integrate operational oceanographic high-resolution models on the Neptune command and control software to increase the response efficiency and hardware security. So, for example, giving the best trajectory for the AUV. and these projects were already accepted for funding. There is another curiosity or another curious collaboration, for example, from multimedia area. We had on board Francisca Gonçalves, a PhD student in digital media, that were interested in collection of sounds from coastal sea, just sounds. So she went there and put hydrophone and sea and just collect sounds of the sea. And this is for a project that aims to promote environmental education through sound art. We have been contacted by people from biology to have contribution to the dolphins monitoring. And the preliminary results indicate also that plume propagation could have impact on dolphins' behavior. And we don't know that before that cruise. And during one day, we also have space to have 2 journalists on board. So it's an opportunity for all labs involved to show a bit of our work and to show off of deploying the AUV. So it's a good picture to be on the national newspaper. So in conclusion, results from several frontal crossings demonstrate the AUV's capability to autonomously detect and survey the front structure of the plume. Salinity remain a consistent identifier, although future missions could use other detection scheme. This study contributes to establish new methods to track and survey coastal features. Could be river plumes, could be blooms, wherever, and also had a very good indications to study the generation of internal waves in these systems. As I take-home message, I would like to highlight that coastal oceanography phenomena like river plumes, coastal upwelling, blooms, there are a lot of them that can be the base for small, local, and opportunistic, objective-orientated technological tests. So the logistic is quite easy. 1 small boat, 2, 3 people, 1 AUV, it's okay. 1 simple AUV, so just CTD. It's very low cost, just the cost of the boat rental if your lab don't have one. And it's an intermediary step between the harbor and offshore operations. That gives the opportunity to engineering and science team work together in a stress-free environment for better preparation for priority and larger projects, and increase the people engagement and more collaboration opportunities for the future, and also give you a better outreach of your lab, and also increase the paperwork planning that is very useful for other projects. So thank you. And that's all of our crew. So 3 people, 2 AVs, and that's it. Thank you.